So last class we talked about the simplest kind of transistor, the junction field effect transistor. So the idea was very quickly review. Okay. So very quickly review. A transistor is a three-terminal device. You have an input, you have an output, and you have some sort of control. Okay, so that's the basic idea. And let's go quickly to the JFET. Okay, so we should understand this fairly well because the next transistor we're going to talk about is a little more complicated in its physics. Okay, so the junction field effect transistor is fairly straightforward. It's essentially two p-n junctions which are reverse biased, sitting against each other. Okay, so you have the structure is fairly simple. You have a lightly doped n-type region. You have a heavily doped P+ gate on two sides. It's symmetric. It's usually connected to each other. So this gate and this gate are connected together. So it's still only a single terminal there. And then you have an input drain. You have an output source. Current flows between the drain and the source, and you control that current by the gate. Okay, so the control terminal is the gate. The input terminal is the drain. And the input is the voltage between the drain and the source, and the output is the current between the drain and the source. Okay, so keep that picture in mind because we will change that as we go on. So, of course, the way it works is, okay, let's skip to the picture, the qualitative explanation of how it works. So, when you have no gate control, essentially it acts as a resistor. Okay, the current just flows. So it's a linear ohmic device. So if you look at the current voltage curve, you get current voltage is a straight line. It acts just like a resistor. Okay? When you start applying a gate voltage, you will see that this p-n junction and this p-n junction becomes reverse biased. So you get a depletion region that grows into the lightly doped region, which is the n-type in this case, the channel. Okay? Now, of course, the depletion region has no carriers, so it cannot contribute to current, so you're actually pinching the channel closed. Okay, so you're reducing the current, increasing the resistance. So that's a basic idea. So if you look at the current voltage curve, it starts bending down. So as you increase the voltage, the current does not increase so much. Okay, that's the idea. Now, at some point, of course, the two depletion regions meet, and that's called pinch-off. Okay, beyond that, you cannot decrease or increase the current anymore. In other words, the current saturates. So you can increase the drain to source voltage, but the current does not change flat in the ideal case. Okay. So basic principle is this. So of course, how does this work as an amplifier? It works as an amplifier because you can have different families of curves by changing the gate voltage. Okay, this is one specific gate voltage. You get one current voltage curve. You change the gate voltage, you get a different current voltage curve. Okay. Which is what's shown here. So you have a family of curves for each gate voltage. And there, if you look at the pinch-off point, you can see there's a nonlinearity. So it's a square dependence. So a small change in gate voltage, let's say going from -3 to -2 volts, has a pretty large change in the current. Not shown here, but you saw the numbers last class. Okay, so that's where the amplification comes. So a signal that goes into the gate with a small amplitude comes out as a current, a signal in the current with a large amplitude. And that's the gain. The gain happens from the input control voltage to the output current. Okay, and that gain is defined as transconductance. Gain in current divided by amplitude of current divided by amplitude of voltage. Okay, keep that picture in mind because we will change that for another device. Okay. Of course, to switch this is very simple, right? You can go at you can increase the negative gate voltage even further and make the current essentially 0. And of course, you can have large current. So that's a switch between 0 and 1, essentially. Okay, so it's switching and amplification. So pretty straightforward. Okay, and we analyzed this. We came up with the equations, and we showed that it's essentially the same. You get essentially a current voltage curve which looks like that. But recall that the output is the drain to source current, ID, the left-hand side of that equation. Just look at this one for now. And you have two inputs, because there are three terminals, remember. And the two inputs are the drain to source voltage, which is typically a bias voltage, or you can call it an input, and the gate to source voltage, which is typically the small signal that goes in, okay, for processing, signal processing or digital processing or whatever. Okay, so you have an input VD, and you have another input VG, and the output is ID, and everything else you know, you can calculate. Okay, and that's how you get these curves. Okay, ID, VD, VG. Two unknowns, two inputs, one output. Okay, so your family of curves. Now, of course, typically, when you want to operate these devices as an amplifier, you have to operate in saturation. In other words, you don't want to be here, you want to be on this side of these curves, so you can have the amplification. Okay, if you are on this side, the problem is that you get distortion in your signal. In other words, if your gate signal, the sinusoid, what you get out could have some noise. It's no longer a sinusoid. It will be amplified, but no longer a clean signal. Okay? If you want to avoid that, you typically operate over here under saturation because the current is independent of the drain voltage. Okay, you will see that if you actually draw the diagram. Okay, so that's the basic idea. Now, we will go to, let's skip that. Oh, and yes, we also talked about the metal semiconductor FETs. Essentially exactly the same principle, except that now, instead of having a P plus N junction, you have a metal semiconductor junction. Okay, so we know if we pick the metal properly, with the work function just right, you can make a Schottky barrier, which is essentially the same as a PN junction. Okay? Of course, the reason to do this is much easier to fabricate. It's much smaller, so you can integrate it easier and so on. Right? Okay. So the equations are all the same, so we don't actually need to do any of this. The key points are, of course, that the gate to channel contact must be a Schottky barrier. But the drain and source metal contacts must be ohmic contacts because you don't want any rectification there. Okay, so you have to be careful how you pick the metals. So in this example, this is gallium arsenide. You pick aluminum for the Schottky barrier, whereas you pick gold, germanium alloy for the ohmic contacts on the source and the drain. Okay. Okay. Now, we talked very briefly about the short channel effects, which was basically what happens when the channel length gets really small. Okay? And we briefly mentioned that. And this is important because almost all the transistors that are made today have very small channel lengths. So this is an example of a transistor. This is perhaps a year or two old. So fairly new. Okay? This is actually an FET. So you can sort of see there is, I don't know if you can see, there's a little bit dark region there. That's the heavily doped region where you make the ohmic contact. Okay, there's a metal contact which is not really shown here. And then there's a gate contact which is right there. Okay, and that's the channel, the semiconductors. Okay, so the question for you, okay, if the channel length is 43 nanometers, so that's pretty small here, okay, and the drain source voltage is 1 volt. You apply a volt across the transistor, which is a reasonable voltage to apply across the transistor. What is the electric field? Okay, how would you do this? I know you know it, so someone, do you know? How would you calculate the electric field? Yeah. Uh-huh. Okay, you have a voltage of 1 volt applied across 43 nanometers, which is a distance. Right? Not you. Someone else? Good. Why don't you talk to your neighbor and see how you would solve it? You're applying a voltage across some distance, right? How would you get the applied field? Yeah, voltage divided by the distance, right? Okay, so it's pretty straightforward here. You have 1 volt divided by 43 nanometers. What is it? Big number, yes, exactly. Yeah, actually, I think I have it here. Yeah, it's about 230 kilovolts per centimeter. It's a large number. Even though you applied a very small voltage, you end up with a huge field. That's a big field there. Okay? So now we need to worry about saturation of the electron velocity in such high fields, which we talked about in third or fourth class. Okay? In all the calculations we have done so far, we assumed that the electron mobility is constant, is independent of the applied field. Okay? So if you recall, electron mobility, mu, multiplied by the applied field is the what?
Drift velocity.
Yes, velocity, the drift velocity of the electron. Right? So if I plot an applied field as a function of the velocity of the electron, I would get a straight line. As long as mu is constant. Right? But we know, and we saw in our previous lecture, that if electric field is too high, this is no longer true. It's no longer constant. It depends on the field, which means that this will start to saturate. Now, once that happens, all these equations that we did no longer valid. Okay? Actually, the transconductance too. Why? Because we assumed this number here. Okay, I gotta go back one more. We assumed this thing to be a constant. Okay? Look at the rho. That's the thing which will change. The resistance of the channel, we assume, is independent. It's a material property, it's independent of the field. But if the mobility actually changes with the field, we know that the resistance has to change. The resistance related to mobility. Okay? Remember, mobility depends on scattering, and that's what gives rise to resistance in a semiconductor. Remember where resistance in a semiconductor comes from. Okay, so that's the idea. So for almost all the transistors that I've made today, these equations are not valid. These equations are nice because it's easy to understand. What's done today, we have to correct for it. Okay, that's the basic principle. It's not that hard to do. Okay, so let's go through it. Okay. So essentially, that's the mobility. The drift velocity of the electron. That's the applied electric field. And this is the linear region where the field is small. And this is the region where the field is large. And this is the intermediate region. And in almost all the cases, you are either in the intermediate region or you're in the high field region, which means that you have to account for this sort of an equation, where the drift velocity is now dependent upon the electric field. Okay? Of course, at some point when the field is very high, it just saturates to a Vs, as shown here. Now, to solve this is relatively easy. You plug this into the calculation for the resistivity and just redo the equations. Okay? The integral changes a little bit, but other than that, it's not that different. Okay? So we can do this if you at the saturation. So in between, it's a little complicated because you have to do the integral. Okay? For our purposes, we'll only study two regions. We'll look at the linear region, which is what we just did, where the mu was constant, and we'll look out here where there's saturation happening. So again, essentially, it's a constant. Okay? But the velocity is a constant. Okay? So the drain current can be related to velocity very simply as the electronic charge multiplied by the electron density, multiplied by the velocity of the electron, multiplied by the area. So electron density times the area just gives you the total number of electrons in that channel. Okay? Per unit length. Times Q gives you the total charges, times the velocity gives you the rate of transfer of charge between the source and the drain. Remember, the electrons are moving from the source to the drain. Okay, so it's pretty straightforward. You plug the numbers in. Q is the same. N is just Nd, the doping concentration. It's N-type material, so simple. Area is Z times H. Z, remember, was the width, the depth of the channel coming out of the plane, and H is the height of the channel. Okay, if you recall the picture we had before, and you plug those in, you get an expression like that, and that's a constant. So now that's your saturation velocity. Okay, which is different than what we saw before. It's independent of voltage, so you have no. Of course, You have one control as a gate. What does the gate do? So that's a question for you. So what does this equation depend upon? Think about the picture we had before.
Charges moving.
Yes, charges are moving. So let's go back to the picture we had before. So keep that picture in mind. So you have a source, you have a drain, okay, and you have a gate here, right? N-type. Okay. These are contacts, so metal. So it is P+, but you don't need to worry too much about it. You have a PN junction here, right? That's your gate. Source, drain, and you have the same thing on this side. Plus, ignore everything else. I'm simplifying it quite a bit. Now, when you apply a gate voltage, you are building a depletion region, right? Now think about that equation and see what does the gate voltage control. Yes, that's right. What did someone say?
The width of H, or the amount of H.
Yes, it is the area. It is H. Remember, H depends upon the gate voltage. Also slightly on the drain, but primarily on the gate. Remember, we derived this. So it is although the current is saturated, you can still amplify it with the gate control voltage. Exactly the same situation. Just that the saturation current calculation is different. That's all. Okay, so keep that in mind. And this is what's shown here. Essentially, this is again the drain current, the output current, as a function of the applied drain to source voltage for different gate voltages. Okay, the current saturates without pinch off in this case. Okay, so you don't actually need to have a pinch off happening before the current can saturate. The current can saturate just because the mobility saturates. Okay, so imagine a situation as shown here where the channel is so small that you may not need lots of voltage here. Okay, you don't need a high enough voltage to actually do pinch off. You can have saturation happening just from the mobility, which is a good thing because you can apply lower voltage on the gate, which means that you have potentially lower capacitance, as you will see on, and you can switch things faster. Because remember, the gate is a control. Okay. Also importantly, transconductance is now independent of the gate voltage. What does that mean? Okay. That means if you look at this curve, it's equally spaced. If I change these by 0.2 volts, the distance that the amount the current changes is about the same. Earlier, it wasn't the case. It was nonlinear. Okay, let's go take a quick look so we are familiar with that. Oops, it's right here. Okay, look at this curve. As I change the voltage, this spacing is getting larger, going up. Okay, but under velocity saturation, that spacing becomes equally spaced. Okay, which means that the change in the drain current as a function of the change of the gate voltage earlier was dependent on the gate voltage. This is the transconductance. Okay, it was some function of the gate voltage. That's why there's a nonlinearity. In the case of saturation, this is a constant. Okay? Or weakly dependent. I mean, if you want to be very rigorous, it's weakly dependent upon the gate voltage. Okay. So those are the main things that happen to keep in mind. There are advantages and disadvantages to both of these. The disadvantage we won't really talk about right now. One of the things you can imagine is if then these things get really small, you cannot really turn the current off completely. You'll always get a little bit of leakage current, which is not a big deal except the fact that this current is a loss of energy, which means you're generating heat. Your circuits will get hot and so on and so forth, which is a problem. Batteries runs out, so on and so forth. So there are other problems which we won't really discuss, but that's this is the modification that we need to apply for almost all the advanced transistors today. So keep that picture in mind. Okay, but make sure you are very clear on the old, the original JFET, because you need to understand the physics of that very well, I'd say. Okay, now we will move on to perhaps the most common transistor out there today. So when someone tells you, the Intel, whatever chip they have, I don't know what the name of the latest ones are, but whatever, it has a billion transistors. When they say that, they mean a metal-oxide-semiconductor field-effect transistor. Okay, this is the ubiquitous transistor out there. The reason we didn't start with this is because it's more difficult to understand. But the reason this is most popular has to do with the fact that this has very clean signal characteristics, and it can be fabricated in an integrated fashion, in a silicon microfabrication process, okay, without gold and things like that. So it's a fairly, I would say, streamlined fabrication process. So in any case, so if you open up your motherboard, you see something like that. That's an integrated circuit. It's fully packaged. Okay, that's what you see. If you open up the packaging and so on, you kind of see something like that. Okay, and there are multiple layers involved here and so on and so forth. And they're essentially a bunch of transistors which are connected to each other with metal interconnects. That's basically it. Okay, there are maybe a few other things out there, but mostly. So if you zoom in on one of these transistors, I mean, you can't see it with your eye, obviously, because they're very small. So you have to take a cross-section with electron microscopes and so on, and you see something like that. Okay, so that's metal-oxide-semiconductor field-effect transistor. Again, we have three terminals. It's the transistors. Of course, you have three terminals. We have a gate, the control, you have a drain, and you have a source. So this is an actual transistor where you can see that's a boron doping. Okay, so boron is what? Group 5, right? So it's a donor. So it's N-type. Boron is group 3 or group 5? I forget now. Arsenic, I think that's P-type. So it is accepted, my mistake. So it's group 3. It accepts, it's P-type. Arsenic, group 5, donor, gives electrons, so it's N-type. Okay? So it's very similar to an FET. Okay, now the difference becomes apparent if you look over here. Okay? So what's the same? Let's go through what's similar. Okay? What's similar is, okay, you have a P-type substrate, which is P-type substrate before. Then you have an N+ region, and then you have a metal contact to the source. So that's from the source. N+P, you have a junction there, PN junction. Okay. On the other side, the same thing. It's symmetric. So you have a drain, N+P. You have another PN junction there. Now, what's different is here. Okay. You essentially have a P-type substrate, then a thin oxide layer, which is essentially an insulator. When you say oxide, it's silicon oxide, silicon dioxide typically. And then you have metal contact. Okay, so that's the main difference. And that makes a huge difference in the physics of the operation. Okay, and that's what we're going to understand. Now, the operation of this device in a very qualitative fashion, of course, you still expect a current flow between the drain and the source. Okay? This is called a drain because it's draining the electrons away. This is called a source because it is the source of the electrons. So the current electron flow goes from the source to the drain, and the current flow goes from drain to the source. So exactly the same as before. But now, of course, you cannot flow through the oxide because it's an insulator. Nothing happens there. The flow happens in this P-type, lightly doped P-type layer. Okay? And of course, if you don't do any, if you look at this and not apply any voltage, okay? We know that this is a N+P junction, so you have a contact potential there, right? So there's an electronic barrier for the majority carriers, electrons to go from here to here. There's a barrier. Remember, there's a contact potential or barrier. So nothing happens, right? No electron flow happens. Same thing over here. Okay, you will see a barrier going from this way to this way, symmetric. Now, applying a gate voltage is not going to change that quite yet. Now, we'll talk about what happens. But before we go into the details, okay, so we can go to the next one. we will qualitatively essentially do the analysis first before we do the math, because the math is a little more complicated than before. Okay? So, in general, there is a nice analogy that one can use to understand the MOSFET. Okay? It's a switch, it's an amplifier. But the analogy, let's see if it makes sense. I want to start with that. So, the analogy is basically shown here. So, this is the MOSFET. Okay, so you have a gate, you have a source, you have a drain, and you have a region. Okay, we'll talk about what these are in a second. But keep in mind, typically, that the gate and the source are connected. So with the voltage. So the gate, when you say gate voltage, it's typically referred to the source. Okay, when you say drain voltage, it is typically referred to the source, and the substrate and the source are typically connected and grounded together. Okay, that's a typical situation. Okay. Now, the analogy is essentially shown here. The source is considered as a reservoir for water. The drain is considered another reservoir for water, and they're sitting at different levels. Think about it as a dam. Okay. And then you have a gate, which is essentially the switch, the gate between the dams. You open the gate, water flows. You close the gate, water doesn't flow. Okay, that's a switch. And it's basically, from an energy perspective, that's basically what happens. So let's see if we can make sense. So the gate to source voltage is the height, in a sense, of the gate over the source water level. So this small energy level. Okay? So if you reduce that gate to source voltage, this water will spill over. Okay, that's the way to think about it. Okay? The drain to source voltage, which is this level to this level, is the water level difference between the reservoirs. Okay? If the drain to source voltage is 0, of course no flow happens, irrespective of whether there's a gate on or off, right? And if the drain to source voltage is negative, flow happens the other way. Okay? So keep those pictures in mind. And so initially, consider the source is tied up to the body, like I said, and to the substrate. The substrate is called the body. The bottom of the transistor. It's typically the wafer on which it is fabricated. Okay. Now, the three regimes of operation, again qualitatively. First, we can think about a cutoff regime. Okay, that's easy to understand when the gates basically turn up, gates blocking the flow of current. Okay, so in that case, electrically speaking, it's essentially the gate to source voltage is less than, as we will see, some threshold voltage. Okay, it's a small value. And the gate to drain voltage is also less than threshold voltage, with the drain to source voltage being positive. Typically, that's the case, meaning the water level on the drain side is always higher than that on the source. Otherwise, you'll have opposite flow, right? So it's meaningless. It's symmetric, so if you do opposite flow, you just switch the terminals, essentially. It becomes the same thing. Okay. This is essentially the off situation, cut off, right? No flow happens. Now, the water analogy is gate is closed, no water can flow regardless of the relative height of the source and drain reservoirs. From the device perspective, let's see what this means. Okay? This region, very small voltage is applied between the gate and the source. So here, nothing really happens. Okay? Basically, it remains as a lightly doped semiconductor, nothing happens. Okay, and you have a very low voltage on the drain to source, but this is reverse. This is a PN junction. Okay, and this is a reverse bias PN junction, right? So this is N plus. That's P. Think about this. P is grounded. S is grounded. So there's 0 voltage across this junction. So nothing happens across the junction. Now, if you think about this junction, this drain is connected to a positive terminal. The P type is connected to the ground. So it's reverse biased, right? This junction is reverse biased, so nothing happens. No current flow happens. So that's the picture electronically, fairly straightforward. Now let's see, so that's why it's shown here. ID is 0. Okay. Now let's see what happens when you apply a slightly higher gate voltage. Okay. This is so-called linear regime, or the triode regime. This is the second regime. In terms of voltages, the gate to source voltage is now slightly higher than some threshold value, okay? Which means that something happens. And we'll talk about what that something is very soon. And The gate to drain voltage is the same as before, or is slightly greater than threshold value as well, and drain to source voltage is greater than 0. Okay? Now, from the analogy that we have, essentially, it's that the gate is open. There's a small difference in height between the source and the drain, and the water flows. There's a small current that flows. But it essentially acts as a resistor. It's a linear regime. So voltage current curve is essentially a straight line. Okay? And there are a bunch of straight lines are for different gate voltages. So this is very similar to what we saw for the JFET before. We had something very similar. Okay? We had different family of curves, but they're all straight lines essentially. The family of curves are for different gate to source voltages. Okay? And you can also plot the drain current versus the gate to source voltage. You can see up to some threshold voltage, nothing happens. Beyond the threshold voltage, you get a straight line. That's the difference. Now we have a threshold involved here. The idea of the threshold is important because now you can see in the off state, you can ensure that there is zero current flowing pretty much. So you can have a pure off. So you can have very good digital logic, which is why these things are very important for CPUs, all kinds of digital logic. Okay? Now, before we talk about the physics of what's happening, we'll come back to that. Again, the electrons drift from source to drain, forming the electric current. As the gate to source increases, the charges increases, okay, which we will see, and the drain current increases. Drain to source increases, electric field increases, and the current increases. Okay, we'll come back to the physics of what's happening in a second. Yes?
The threshold voltage depends on what?
We'll come back to that. Yeah. Think about that. It has to do with creating carriers in the channel here. And that's basically what we'll talk about in a couple of slides. But I want you to get a qualitative picture of the three regimes first before we do that. The third regime is the typical operation for amplification, okay, the saturation. Okay, in this case, the gate to source voltage is greater than some threshold, and the gate to drain voltage is now less than some threshold, and the drain to source voltage is greater than 0. What does this mean? This means that the gate is open. From the water analogy, this gate is open. The water flows from the source to the drain, as shown here. But on the drain side, there is free draw. Essentially, the total flow is independent of the reservoir height. So this is always higher than that, which means that if the gate is open, this flow can happen irrespective of the drain to source voltage. In other words, the drain current becomes independent of the drain to source voltage, which is the same as what we've had before, the saturation. Okay? So ID is independent of EDS. So in the current voltage curve, you have something which goes up. Now this is the linear regime, and out here you get saturation. As drain voltage increases, nothing happens to the current. Same as what we had for the JFET. Okay? So three regimes. You have cutoff, linear regime, saturation. Okay? Now we have to see what that means physically. Okay? Now the family of curves pretty much looks the same as we had before. Okay? ID, VD, and you have a bunch of nonlinear curves which is controlled by the gate voltage. But in this case, it's positive, but that depends on the polarity of whether it's N-type, P-type, and so on, right? But anyway, we'll come to that. In this case, there is a saturation that happens, which is not really pinch-off. Okay? We will talk about that, but it's very similar in effect to pinch-off. Okay, so what happens what happens for the device which makes it to switch between these different regimes? Okay, so for the cutoff regime is easy to understand because the two PN junctions are reverse bias, so it's trivial. There's nothing to be there. For the linear regime, what happens? We said that the gate voltage is beyond some threshold. Okay, what does that threshold mean? Okay, so if you look at this region right here, okay, this is a P-type region, lightly doped P-type region. Okay, you end up creating when you apply a positive voltage on the gate. Okay, in this case, when you apply a positive voltage on the gate, you attract negative voltage. You induce a negative voltage on the other side of the insulator. Okay? So the picture is the following. You have a gate, which is essentially a metal. You have an insulator, which is the oxide. And then you have, in this case, a p-type semiconductor, silicon. That's it. So you apply a positive voltage. You create positive charges here. Okay? Of course, this is an insulator. Nothing happens here. You start attracting negative charges here. Okay? You apply positive charge here to induce a negative charge. Okay? These negative charges come about two ways. First, the p-type material has lots of holes. Okay? First thing that will happen when you have positive charge here is that the holes will get repelled. Okay? They move away from that interface. Right? Positive charge, they repel. When that happens, you expose the acceptor ions, which are negatively charged. Okay? So you expose uncompensated acceptor ions. It essentially creates a depletion region. Right? You push the holes away, you pushed away the carriers, it's a depletion region. Okay? That's basically this light gray region. Okay? It's a depletion region. But that's not sufficient for carrier flow, right? Because the depletion region means there are no carriers. Current cannot flow. That's the threshold. So you need to do something else. You need to apply a bit more voltage for something else to happen for carriers to exist. Okay? That's the reason for the threshold. We'll come back to that. Okay, so we have a situation where we applied some voltage, we created some negative charges here, we pushed away the holes. Okay, if you increase that voltage further, you have to, at some point, you will expose quite a few of these ions, but that's not sufficient. Okay, because you need to match the charge density on each side, and we'll come to that later on when we solve this. The only way to do that is to push away so many holes that you make this region locally n-type. Okay? In other words, you have pushed away so many holes here that the electrons that, of course, exist here now start dominating over the holes. Okay? Now, how does that happen? Because the electrons from far away can get attracted here. So locally, you can get a very high concentration of electrons. Of course, even in a p-type material, you have plenty of electrons. Well, the only thing is that you have a lot more holes in electrons. So if you apply a positive voltage, you start pulling the electrons closer to the interface. So locally to the interface, you make the material n-type. So you convert the p-type to n-type. Okay? And that's called inversion. Locally, just near the interface. Okay? And that's this light blue region. It's called an inversion layer. Okay, now you have electrons. Okay? Now if you apply a voltage between these two terminals, current can flow. Yes?
So you wouldn't even need any donor atoms in the p-type material, because you, like...
Yeah, go ahead.
If I'm understanding correctly, then basically you can just have, in silicon, have the electrons come up there, and it would act like an n-type.
Except that, remember, you need a reverse bias junction over here. Okay? You cannot just have a silicon and just a gate voltage. You need and ohmic contacts here. You need to have a reverse bias, otherwise the current will flow without any gate voltage. So you need to have a PN junction there.
Yeah, but like in the p-type material,
yes?
You wouldn't need any donor atoms.
Well, p-type material means you already, that's correct. You don't need donor atoms, that's correct. But you have acceptor atoms, that's correct. Yeah, you don't, because in any material you have electrons and holes all the time, right? The p-type just means you have increased the holes more than compared to the electrons, but you still have some electrons. And what happens here is that you collect all the electrons in the bulk to come to the interface. So locally you have made it n-type. Okay? Now it's very simple to understand. Now what you have is essentially you have a voltage between the drain and the source, and you have a channel which can conduct electricity. Electrons. That's it. Right? That's why it's a linear regime. You apply voltage, current flows. It's almost like a resistor. A straight line, current voltage curve. Okay? Now the threshold comes up because you need to have sufficient number of electrons here for the channel to happen, which means you have some minimum voltage that you need to apply. That's the threshold. That's the physical meaning of the threshold. Okay? Now, of course, you can have a pinch-off situation here as well, because just like in the FET, the channel is a distributed resistor. As current flows, there's voltage drop, right? Because the electrons are moving, but it's not a superconductor. You have some loss, so you have voltage drop, which means that the voltage on this end will be higher than the voltage on this end, right? The drain to body voltage. I'm talking about just drain to source voltage. The body and the source are grounded, so it's the same. Okay, so you have voltage drop, which happens here, which will basically decrease the electron. So this is positive, right? Remember, this is a reverse bias junction. This is positive, which means that you will deplete the electrons here. Okay, which means that you will end up having a pinch off of the channel. It's a different physical mechanism, but you will have the same result. Okay? You will reduce the carrier concentration here, and this here it will be maintained. At some point, the current pinches off, and you reach saturation, and that's the pinch off starts, current saturates, and that's the situation. Of course, the gate has to be greater than threshold because you need to have some sort of channel, and the drain voltage is now gate VG minus VT, which is right there. It's barely at the threshold. That's what that means. Okay? Because right here it will be the voltage you have to consider is the difference between VD and local voltage right at that point, which of course will be determined by the applied voltage VD. Okay, it's exactly the same as we had in the FET. Now, of course, you can continue applying higher drain voltages and you get strong saturation, which means that this pinch-off region goes bigger and bigger. Okay, it's exactly the same as before. Current is still saturated, but you have other effects that you have to take into account. Just like we saw previously, if you had a short channel, here you're reducing the channel length, so you have some effect that you can expect to see. Okay, we'll talk about those later on. Okay, so that's a qualitative picture. Okay, now to do the more quantitative analysis is more complicated, but before we do this, we need to also understand this from the energy band perspective. In my mind, that's probably the easiest way to, because now we should be very familiar with energy bands. This is what you're familiar with. So from that perspective, it should be the easiest way to understand than what I just mentioned. So let's look at that. When you have no applied voltage, the bands are very straightforward. Okay, you have a metal. So you have a metal. Okay, the metal, we know how to do it. You have a Fermi level up to which all the electrons are filled, all the electronic states are filled, and you have vacuum, right? So you have a work function. Okay. We'll come to that in a second. And next to it, we have an oxide. An oxide is an insulator. Remember, it has a huge band gap. So we haven't shown the valence band here, but the conduction band is very high up. That's it. So it's a big energy barrier. Okay? And we define what's called a modified work function, which is essentially the difference between the Fermi level of the metal and the conduction band of the oxide. And the assumption is that the oxide conduction band is so far away that it's about the same as the regular work function. It's usually a little bit less, but it's good enough, right? That's a reasonable assumption to make. On the other side, you have the semiconductor. In this case, we have a p-type semiconductor, so you can see the Fermi level is down here, closer to the valence band. It's lightly doped. Okay, the conduction band's there. EI is the intrinsic level. Okay, so far so good. Now we also define a modified work function for the semiconductor, which is essentially the difference between the Fermi level of the semiconductor and the vacuum level, or the conduction band of the oxide. Okay, so far so good. Now, we can also define a parameter phi f, which is the difference between the intrinsic level and the Fermi level, which, of course, defines the carrier concentrations, right? If this Fermi level goes down, you have more holes. The Fermi level goes up, you have more electrons. Okay, so this phi f is just a measure of the carrier concentration in the semiconductor. Okay? So, another way to think about this is a parallel plate capacitor, right? You have a metal, you have a dielectric insulator, and then you have something on the other side, which is a semiconductor, but if it's heavily enough doped, that's just a parallel plate capacitor. Okay? And the capacitance of this turns out to be very important for switching, as you can imagine, because remember, this is the gate. Okay? This is where the small signal comes in, and how fast those carriers move And it determines the capacitance, and that will determine how fast you can switch this device. Okay? So it's very important to calculate the capacitance of this particular pseudo capacitor, in a sense. Okay? Now, what happens when you apply a voltage? So that was equilibrium, no applied voltage. So in this case, you apply negative voltage on the gate. Okay? What happens? Essentially, when you apply negative voltage on the gate relative to the semiconductor, the Fermi levels split. Right? No longer flat. So you have a Fermi level which goes up on the metal side. Fermi level goes down on the semiconductor side. The difference between them is the applied voltage. We know that. So far, so good. If the Fermi levels split, that means that the bands have to bend. Some of the potential falls across the oxide, so you get a band bending of the oxide. You get some field across the oxide, which is just like a parallel plate capacitor. Right? So the capacitor, two metals on each side, and imagine that this region is filled. It can be filled with anything. It can be air, or it can be an oxide. It doesn't matter. It's in the insulator. You apply a voltage, you get a field across it. Right? So the bands bend. That's basically what's happening over here. But since this is not a metal, some of the voltage also gets dropped across here, so you get a band bending here also. So you have the applied voltage, some of it comes across the oxide, some of it comes across the semiconductor. Okay? Now, so that's the applied voltage, QB. So when you apply a negative voltage, the charges are deposited on the metal. Okay? So you have a negative terminal connected, so negative charges are deposited on the metal, which induces positive charges on the other side of the semiconductor, which is another way to think about. When you say positive charges are induced on that side, which means you're pulling in the holes. Okay? Which means that the local concentration of the holes are increasing, which of course is consistent with the band diagram you see, that the valence band is getting closer to the Fermi level, which means that the hole concentration is locally increasing. Okay? So it's consistent with the picture of the electrostatics. Okay? So the positive holes are attracted to the interface here, and there's accumulation of holes at the interface. So you get this bending upwards. Okay? Of course, there's no current flow in the semiconductor, right? Because this is an oxide, it's an insulator. It's like a capacitor, there's no current flow, which means that the Fermi level in the semiconductor has to be flat. Cannot bend, right? Remember, we proved that the Fermi levels at equilibrium is flat, and that was proved by making the assumption there was no current flow. So the bands have to bend up, so there's accumulation of holes here. Now, what is the situation? This is the situation we didn't actually talk about because it's a negative voltage on the gate. It's the opposite of cutoff. Okay? So remember, this diagram goes upside, rotated 90 degrees to get that. Okay? In that situation, what we have is basically lots of holes here in the channel. Okay? Which means that if you apply voltage, of course current will flow, but the gate has no control essentially. Increasing the negative gate voltage increases the hole concentration, but the current really doesn't change very much because you already have lots of holes. The change in the hole concentration is small. So you have no control essentially. Okay? This is similar to forward biasing the JFET, if you recall. I had asked you about that. Okay? Now, applied positive voltage on the gate gives you the right condition. Okay? If a small positive voltage is applied, then you have the cutoff regime, or the linear regime, if you are slightly above the threshold. But let's start with cutoff. Okay? So in this case, when you apply a small positive voltage, you get positive charges here, and the bands bend the opposite direction, so we're familiar with this. The Fermi level of the metal goes down, Fermi level of the semiconductor goes up, and the difference is the voltage. Here the bands bend down, this Fermi level has to be flat. This is positive charges accumulate here, so now you push away the holes. So this material, the hole concentration goes down as the bands bend down, and at some point you attract enough electrons that now this becomes more N-type. So if you look at this semiconductor, right at the interface, it's N-type. As you move away from the interface, it becomes P-type. Okay? It's an interesting situation because now you have what's called a graded p-n junction, right? It's an induced p-n junction. Okay, so it has some very interesting properties, but we won't really talk too much about it. But you can think about that as depletion. So in this case, it has more negative charges are induced by repelling the holes and exposing uncompensated acceptors. The bands in the semiconductor bend down and charge carriers holes are depleted at the interface. Okay? So as long as you have a few electrons and some of the holes are gone away and you have the linear regime. Okay? Well, you can have cutoff if you don't have enough carriers. So you have some regime where you have no current flowing. At some point, when you increase the gate voltage further, in the negative, in the positive direction in this case, you get enough carriers that you start turning on the current. Okay? That's the idea, which is what happens here. Okay? That's the inversion condition. The applied gate voltage is even more positive. The bands bend even more, and the key difference is right there. Okay? The intrinsic level now bends below the Fermi level, which means that the material now becomes N-type. Okay? There's more electrons at the interface than there are holes. Okay? Idea is simple. So you have an inversion here. The bands bend down so much that the p-type material becomes N-type. Another way to think about this, by the way, is almost like the 2D electron gas we saw before. The electrons are essentially trapped in some potential well. So this forms a potential well, very similar to the quantum well we saw 2 classes ago. Okay? This is an energy barrier for the electron. The electrons are up here. This side, of course, you cannot go across because it's an oxide. This side, you see an energy barrier formed by the band bending. Okay? That has some important implications for the mobility of the electrons, as we saw for the quantum well. Yes?
So the p-type material sort of phases into N-type?
Yes, exactly.
So if I'm understanding correctly, then the resistivity would kind of increase as you move away from the...
That's a good point. But think about which way the current is flowing.
Toward... Like
yes, the current, in this situation, the current is flowing out of the plane of the screen. Yeah. Right? It's not going through the substrate. Why? Because you have an oxide. You have an insulator. The current cannot flow left to right or right to left.
But the resistivity of that flow...
The channel, yes. So it forms a channel. So think about this as a sheet coming out of the plane, and that's a channel. Okay, right here. You get a channel right here coming out. The current flows out. Or in, doesn't matter. But yes, the resistivity of that channel becomes important, which is, of course, determined with the mobility, and we'll talk about that later. Okay, so that's a basic idea. Okay, now what has happened is that you can use the gate voltage to control the band bending, which changes the carrier concentration, which of course changes the current. That's a basic principle of operation. A little bit different than the FET, but not that difficult to understand. Okay, the holes are repelled in the semiconductor and the interface becomes N-type locally. This inversion layer forms a conduction band for the MOSFET. Okay, which is the channel. The channel is essentially coming out of the plane. Okay. Now let's do some math to understand this. So it becomes a little complicated, but let's walk through it a little bit. Okay. So we're looking at the inversion condition, which is the operating regime of the MOSFET. Okay? So let's just look at the bands first, because that's easy to understand. We have the valence band, you have a Fermi level that's flat, you have an intrinsic level, you have a conduction band. Okay, as I said before, the difference between the intrinsic level and the Fermi level is this phi f, determines the carrier concentration. If the phi f is positive, there are more holes. So the phi f is negative in the way it's described here, defined here, it becomes N-type. Okay, so pretty straightforward. On the oxide side, you don't need to do anything because there are no carriers, right? You can totally ignore that. So you start with x equals 0 at the interface and increasing that way. Okay, so first thing we can do is under strong inversion, the region we have to make some criteria for strong inversion, and the reasonable criteria that we can make is that at the interface the material becomes as N-type as the material is p-type far away. In other words, you are saying that you want as many electrons at the interface as there are holes far away from the interface. Okay, that's a qualitative assumption. That's a reasonable assumption to make. Not an assumption, but a point of reference to make. Okay? So under strong inversion, we claim that the region near the interface is as strongly N-type as the bulk is p-type. This essentially means that this difference at the interface, phi s, difference between the intrinsic level far away in the bulk and the intrinsic level near the interface, okay, is given by 2 times phi f, where phi f is this difference here. Okay? In other words, what we're saying is that the band from here bends about twice as much down. Okay? And that's equal, of course, equal to 2 kT over Q log of the acceptor concentration divided by Ni. Okay? Because that is just that from there. Okay? This phi f is determined by the hole concentration in the bulk. Okay? So that's just that. Now the electron concentration locally, so we can calculate that as essentially N. The electron concentration is given by that term and can be written as N naught e raised to phi, which is this local difference between the Fermi level and the, the local intrinsic level and the bulk intrinsic level. Okay? So as the bands bend, the electron concentration increases. As this phi increases, there are more electrons exponentially. Okay? Where N naught is the equilibrium electron concentration. Okay. So you can do the same thing for the holes. We won't go through that, but exact same thing. Now, of course, now we have a way to locally say, okay, there's so many holes, there's so many electrons, as a function of the bands. Okay, that's straightforward because we know how to do that. Now we need to relate the concentrations of these holes to the applied voltage. So remember, our goal here is to say, okay, if I apply this much voltage, how many electrons come here so I can calculate what's the current this way. That's basically the goal. And we are just doing the first part of it. Okay? So we need to relate the electron or hole concentrations to the applied voltage, which we have to some extent because the bending depends upon the applied voltage, right? So the logical progression here is pretty straightforward. Okay, so to calculate how the charges change with the applied voltage, we have to solve Poisson's equation. Remember, Poisson's equation relates charges to the applied field, okay, from our electrostatics. So that's essentially the second derivative of phi because that is the derivative of the field, right? Okay, so maybe you guys forgot, but remember Poisson's equation relates the gradient of the field to the charge density. That's the charge density divided by the epsilon, which is the dielectric permittivity. You can ignore that. Field is what? Voltage divided by distance, or the differential, right? The gradient is just taking one more. This is one dimensional, so you can just do that. Right? So that's just that. Of course, we know that B is basically proportional to phi, the band bending. So you can just plug that in. Oops, that's my phone. Okay. So that's where that comes from. There's some signs involved. The sign comes out because the bands are defined opposite to the voltage, energy, right? This is defined in terms of electronic energy. But other than that, the logic is straightforward. So the second derivative of phi is minus rho over epsilon. Okay? Now we know rho is pretty straightforward to calculate because there are 4 terms. 2 positive terms, 2 negative terms. The charges from the ions, the acceptor ions and donor ions, if there are any. So you have donor ions. This is the exact same as the first question in the midterm, for instance. You go back and look at it. So you have the donor ions, acceptor ions, holes, electrons. Okay, plug that in. Put everything in there. And we know that you can ignore the donors, ignore the acceptors if there are none. The donor concentration is equal to the, you can ignore the donors because it's p-type, and the acceptor concentration is equal to the equilibrium hole concentration. Okay, so you know these numbers, you plug those in, which is P naught in this case, and the expressions for P and N come from here, which we just talked about, plug everything in, and you have a relatively straightforward differential equation, which relates the band to position, band as a function of x, phi as a function of x. Okay? So remember, what we have done now is we are trying to solve for the curvature of the band. How does this curve? Because if we know that, we know the relation of the voltage. Okay? Because the curvature band is related to the voltage. Okay? So to solve this is not that difficult. You do an integral where you integrate, you can simplify the differential equation as shown here, and then you do an integral from the bulk far away in x to the interface where you have some applied field. That, by the way, is the negative of the field. On the other side, again, you go from 0, where this phi is 0 in the bulk, as you can see, and near the interface is phi s. So that's phi s. Well, phi locally, 0 to phi. Okay, you do the integral and you get an expression like that. Now, of course, this is the electric field, like I said. So the solution you get actually is for E squared. You see that, right? This is just integral of x dx. Okay, that x is just There's a negative sign there. Okay, so you get that expression, not that difficult. Now you can get the electric field of the interface. Now if you know the electric field, of course you know the voltage and so on. Yes?
The P-type material becomes an N-type when the intrinsic level crosses the Fermi level?
Below the Fermi level, yes. What does that mean? The difference between the Fermi level and the valence band or the conduction band tells you whether it's P-type or N-type, right? If the Fermi level is closer to the valence band, it's P-type. And it's closer to the conduction band, it's N-type. When the intrinsic level falls below the Fermi level, that means the Fermi level has gone closer to the conduction band. Means it has become N-type.
And can it bend so much that the conductor level crosses the Fermi level?
Yes, you can. The design is such that it can. It's a good question because it's a lot of band bending, which means you need lots of field. Okay? It's a very good question from a practical perspective. To get a lot of field, it doesn't mean you need a lot of voltage, as we just saw for short channel. You can make the gate oxide really, really thin. If I go back here, if you make this region very thin, I can get this band bending at very low voltages. Right? Remember, we calculated with 43 nanometer channel length, you had a voltage, electric field of 230 kilovolts per centimeter. 1 volt applied. The oxides that are used in transistors today are like 1 nanometer. Very, very small. So you can get this band bending relatively easily at low voltages. That's a very important point, turns out. Okay, so so essentially now you have the electric field at the surface as some complicated equation, and we defined a new length term here, which is the Debye screening length, which has an important meaning in electrostatics, but we won't really dwell on it too much. Okay, so now you have the electric field, so we can plot that. Oh, so of course we want to plot the charge density. Okay, electric field is related to charge density as shown on the top there. The charge density at the interface is essentially minus of the electric permittivity times electric field. Okay? That's the definition. So now you can plot for different situations. Phi s is the applied surface, the interface voltage is the horizontal axis, and the vertical axis is this surface charge density. Okay? Now, as you have, let's start at 0. When you have 0 volt applied. So the phi s is somehow related to the applied voltage. We'll relate that soon. But let's just see how the dependence works. So when 0 volts is applied, okay, what do you expect the charges to be? It should be 0, right? There are no induced charges, nothing happens. So the charge density is essentially 0. It goes to 0. There's a singularity there in the equation. Okay? Now as you make it a little bit negative, you start attracting holes. So the hole concentration increases it becomes more p-type than equilibrium. That's what's shown here. Ps at the interface is greater than Na. And it increases exponentially. And that regime is what we talked about at the very beginning. It's called accumulation. It's below cutoff, essentially, where you have no control of the gate. Current flows all the time. Okay, there's very little control. Okay, the difference in the charges are too small to really control it with the gate. Okay. Now, on the other side, as you make the gate voltage more negative, you're depleting it. So you're pushing the holes away, you're exposing the ions. This is the so-called depletion region where you have slow increase. Okay, something like a square root in this case. And at some point, you start inverting it, which means you start creating more electrons, a weak inversion. Make a little bit n-type. And at some point, it becomes strong inversion. You attracted so many electrons that it becomes very strongly n-type. And that can increase exponentially. Okay? This part is the so-called triode or linear region that we saw in our water analogy, and that's the saturation region, when you actually have a channel. Okay, so that's the quantitative picture of the different regimes as you apply the voltage. Okay? Now we have to relate, this is with respect to the surface voltage, the interface voltage. Now we have to relate the interface voltage to the actual gate voltage, because that's what you actually apply. Okay? So in order to do this, we have to model this as an ideal capacitor, and it's, like I said, it's essentially a parallel plate capacitor where you have metal on one side, oxide, and on the other side you have a semiconductor. Okay. So we can model this fairly carefully. The band diagram is exactly the same as before. In this case, you have strong inversion. The applied voltage is very strongly positive, so you pull the bands down so much that you have a nice n-type channel right there. Okay. Now, the applied voltage, as I said before, is dropped across the oxide because you have an insulator. So some of the voltage, if you drop, gets dropped across the oxide, and some of the voltage comes across the interface on the semiconductor side. Okay? And if you draw the potential as a function of position, you have a constant potential in the metal, and as soon as you hit the oxide, you start having a linear drop because the oxide has cannot have any charges inside, so it's just a straight line, just like a capacitor. Okay? Fixed field. Straight line means the field is constant. Okay? But in the semiconductor, we have band bending, which is non-linear as we saw. It's not a straight line, so you have some complicated equation that defines that. So that's the phi s, the voltage across the semiconductor. That's the Vi, which is the voltage across the insulator, the oxide. Okay. Now, to calculate the this voltage drop across the oxide, we have to look at the charges, which is basically what's plotted here. This is the charge density on the metal side should be equal to the total charge on the semiconductor side. No charges in the oxide because there should be total neutrality, right? Total should be equal to 0. On the semiconductor side, we know that the charges should be whatever charges come from the uncompensated acceptor ions minus whatever comes from the electrons that have been attracted. So they have two opposite charges. Okay? So you have a big charge density right at the interface of the metal and the oxide. No charges in the oxide. And then you have charges coming from the inversion, which is electrons. And you have charges coming primarily from the depletion, which is shown here, which is from the uncompensated ions, minus the electrons. Okay? So you have a situation like that. And then the voltage is related to the charge essentially by the electric field. Okay? If you plot the electric field, which is essentially the, remember, electric field is charge is minus epsilon times electric field, so electric field is just in Q divided by epsilon s. Okay? Or the integral of that equation, just like here. Right? So you get a constant electric field across the oxide, and then you have a linear drop in the electric field in the semiconductor side. Okay? And from those two equations, you can calculate what the potential drop across the oxide would be, where it actually acts as a capacitor. So you have a voltage drop is given by the surface charge, surface interface charge, times d, the distance, the thickness of the oxide, divided by the epsilon, the permittivity of the oxide. Okay? And of course, that can be written as charge divided by capacitance. Okay? And this is the oxide portion of the parallel plate capacitor. We know that there will be some capacitance associated with the charges here as well, because we saw that for the p-n junction. So this is only one part of the capacitance. So you have one more term of the capacitance, which we'll talk about next week. But so you can think about this oxide capacitance per unit area as the charge storage capacity of the parallel plate capacitor, ignoring the semiconductor, essentially. Okay. Okay. Well, stop here, and I will post the review problems from this chapter online. So make sure you try to do them yourself. Okay. I haven't actually posted them yet.